Rosalind Franklin,
Mary Somerville,
1920 to 1958.
Eleanor Davies Collins, 1870 to 1870.
She worked using X-ray crystallography to gather the data to understand the structure of DNA, and her data allowed her and others to discover the structure of DNA. She hugely inspired me as a young potential scientist. Rosalind Franklin, X-ray crystallographer, 1920 to 1958. Rosalind Franklin,
1831. Arthur Ayrton, 1858 to 1973.
Rosalind Franklin, X-ray crystallographer, 1920 to 1958.
My name is Herbie Clark, and I am the production manager and designer, and I work for Electric Voice Theatre.
And I'm Frances M. Lynch, and I'm the artistic director. So we're a small company of singers who specialise in contemporary music for voice and electronics in a theatrical context.
Tonight, you will hear the voices of many of the singers who have worked with us on pre-recorded music.
They are
Jenny Miller,
Penny Osmond,
Margaret Cameron,
Simone Ibbott-Brown,
Alice Privet,
David Shepherd,
Julian Stocker,
and Gwion Thomas.
Oh, and you.
Oh yeah.
It has always been important to us to make accessible music and make it as possible for our team to include things like the BSL interpreter, Lauren Lister. Our live performances are designed with integrated British Sign Language and audio description.
We've been touring the UK with our Minerva Scientifica project since working on the Franklin effect at King's College London all those years ago, which gave us an incredible springboard to investigate many women scientists past and present who've lived or worked in our islands.
And to tell their stories using the music of women composers, also from the UK, much of which is commissioned, and a lot of it is written by Frances, with children and adults that we worked with while we were on tour, celebrating their local heroines, past and present.
We're very grateful, of course, to the Arts Council, who are providing us with emergency funding to undertake this work online as part of a wider project called Minerva Scientifica Connections. I nearly forgot the word connections, which is the whole point of the project. And to the Performing Rights Society Foundation, who are funding me as a composer.
Our contributors this evening include many illustrious individuals from the world of science and art, including our chair, Dr. Birgit Ahrens, who is a British Academy postdoctoral fellow at the University of Bristol and an Electric Voice Theatre trustee.
Thank you very much, Frances and Herbie. I'm really honored to chair tonight's program and would like to welcome our audience as our contributors tonight. We're here to celebrate the life and work of Rosalind Franklin, who was born 100 years ago today on 25th of July, 1920. Rosalind Franklin is one of the 20th century preeminent scientists. Rosalind Franklin's work could not be more pertinent today. Most of us will know Franklin's imaging work that was catalytic to unraveling the structure of DNA. But this, as you might be surprised to hear, presents only a fraction of her legacy. Her work on the structure of DNA sits alongside other bodies of research, notably and particularly pertinent to us today, her work on viruses. Her work in so many ways mattered to society. In a couple of presentations, we will hear from historian of science Patricia Farah and molecular biophysicist Brian Sutton about Rosalind Franklin's varied research areas as a woman scientist working in London and in Paris. Her research is not only of continuing relevance today, it also matters to artists. Rosalind Franklin's life and work has inspired composers, musicians, and visual artists alike to reimagine her working in a laboratory environment and to reimagine her visualization techniques through which she made manifest the seemingly invisible contributors to life. Following the presentations and a conversation in which you, our audience, are invited to participate, we are excited about the world premiere of Virus in Molecular Mode, a music composition and film by Francis M. Lynch and Shelley James. We are then joined by one of Britain's most respected composers, Shirley Thompson, who we are honored to say will introduce yet another premiere tonight, The Franklin Effect. Enjoy this varied program inspired by Rosalind Franklin, and we will meet at points throughout the program. So I've got the pleasure to introduce our first speaker this evening, Dr. Patricia Farah, who is Emeritus Fellow of Clare College, Cambridge, where she teaches history of science. A former physicist, she is particularly interested in the difficulties experienced by women in science, and her most recent book is A Lab of One's Own, Science and Suffrage in the First World War. As well as appearing in TV and radio programs, such as Melvyn Bragg's In Our Time, Patricia Farah has published many journal articles and books and regularly gives public lectures. However, before Patricia starts her presentation, you as our audience, you can participate, and any questions that you might have, could you please put them in the chat function that you see at the bottom of the screen? And we will have a conversation and discuss questions after the second presentation. So anything that comes to mind, please do put it in the chat and we bring it together later on. The floor is yours, Patricia.
So welcome everybody to this short presentation I'm going to give on Rosalind Franklin. So during her short life, very few people outside science had heard of Rosalind Franklin. But since her death, she's become a legend. There's a university in Chicago that's named after her. There's even a Mediterranean cruise ship. And she's particularly famous for her work on the double structure of DNA. And she's become a potent symbol of male prejudice. But as this plaque suggests, she was pioneer not just in the study of DNA, but also in the study of molecular structures, including DNA. She carried out very important research into several other topics as well. And what I'm going to do in the next few minutes is give you a brief outline of her life, but I'm going to move away from the controversies surrounding DNA to give me a more realistic picture of what she achieved. So she was born in London exactly 100 years ago today. And these pictures, I think, illustrate quite well how the London then is sort of familiar, but also different. And the photo at the bottom shows her local tube station as it was then, Notting Hill Gate, which is where she lived. Franklin's large family was extremely important to her. And she belonged to an extended and very affluent Jewish community. And that's why now she's buried here in the Jewish cemetery at Willesden with her relatives. As a child, she was very intellectually alert. She went to a high-powered school, St. Paul's, where she was often near the top of the class. And one day she came home enthusing,
We spent the whole arithmetic lesson today with a lovely discussion about gravity and all that stuff.
And she was also thrilled when her mother showed her how to develop photographs, perhaps a foretaste of what was to come. And then she went to Newnham College at Cambridge. That's one of the 2 women's-only colleges there. And one of her friends remembered,
Oh, she had very high standards and expected others to have the same.
That is, of course, an admirable characteristic, but she was sometimes so hard on herself that she panicked about exams and she underperformed. And some of the men she worked with misinterpreted her attitude and criticised her for being difficult. She went to classes in the Cavendish Laboratory in Cambridge, which is where Francis Crick and James Watson later built their first double helix model. And she started a PhD, but she had a strong social conscience, and she told her father,
I would rather have war work now and a PhD later.
So during the war, she carried out very important research into coal and graphite, which was particularly important for the filters in gas masks, the PPE of the era. So she got her PhD, and then she landed a research position in Paris, which she absolutely loved. It was there that she became a skilled X-ray crystallographer, and she was treated as an equal in the lab. But after a few years, she decided to go home, and she found a position at King's College London. London was still in ruins, as you can see from these pictures, and there was also a bomb centre right in the middle of the quadrangle at King's College. As far as her work was concerned, things started going wrong right from the very beginning because her status was never clearly defined. Unlike in Paris, she was discriminated against as a woman. Now, this plaque suggests, rather misleadingly, that she worked in the team. At the bottom, you can see Maurice Wilkins' name, but she had frequent quarrels with him. Her true collaborator is named at the top right, Ray Gosling, who was her PhD student, who took this famous photograph 51 that revealed the double helix structure of DNA. But she hated the atmosphere. She hated the atmosphere there and had secured a different position. Sorry, am I the only person hearing this? Has it stopped? Did everybody hear that noise?
Yes.
It's
Okay,
fine.
It's
Fine now.
Okay, I'll continue. So I was just talking about, here's a photograph 51, which was taken by Ray Gosling. It was a famous photograph that revealed the double helix structure of DNA. But she hated the atmosphere at King's, and she'd secured a different position before Crick and Watson published their DNA model. They announced their suggestion in Nature in April 1953. People often hype this up as the most important discovery of the 20th century, but at the time, nobody took that much notice. British people were far more interested in the news that Edmund Hillary and Tenzing Norgay had climbed Mount Everest. Unlike Franklin, Norgay was marginalised by the use of his first name. But by then, Franklin was happily embarked on a new project with John Desmond Burnell at Birkbeck College, analysing the structure of the tobacco mosaic virus. This was economically important because crops were being ruined, you can see on the right, but was also a landmark study in the new science of virology. And when she finished mapping that virus, she moved on to another crucial project, the Polio Virus, which was devastating so many lives in the 1950s. By now, she was a world leader in virology, invited to international conferences, but she was already also suffering from cancer, and she died on the 16th of April 1958. And this plaque is on the block of flats in Kensington on the left, where she lived for 7 years. Now, after her death, two major events transformed this talented young virus expert into a symbolic victim of male oppression. So the first one, 1962, this is part of a telegram to Francis Crick, announcing that he, Watson and Wilkins had been jointly awarded a Nobel Prize. And many campaigners protested that she should have been included too. But worse was to come. In 1968, Watson published The Double Helix, a scientific bestseller in which he revealed that Wilkins had secretly shown him Franklin's photo without asking her permission. This was the vital clue he needed.
The instant I saw the picture, my mouth fell open and my pulse began to race.
Throughout the book, Watson patronisingly called her Rosie, which was not her name, and he commented on her appearance rather than on her scientific skills.
she did not emphasize her feminine qualities. There was never lipstick to contrast with her straight dark hair, while at the age of 31, her dresses showed all the imagination of English blue-stocking adolescents.
Many people, including Crick, were furious that he should denigrate her after her death. So as a consequence, Franklin's become an extremely famous role model for female scientists, but for the wrong reasons. She did fight for gender equality, but she deserves to be remembered for her lifetime achievements, not for media manipulation after her death. So this is my favourite photo of Rosalind Franklin because it shows her as a dedicated scientific expert. And in this COVID year, the tribute on her grave testifies to her enduring significance.
Scientist. Her work on viruses was of lasting benefit to mankind.
Thank you very much, Patricia, for starting our evening off and for starting our journey into Rosalind Franklin's life and research and her enduring legacy. It's really nice to get a bigger picture of her life. I would now like to introduce our second speaker, Brian Sutton, who is Professor of Molecular Biophysics at King's College London. He studied chemistry at Oxford University and then trained in X-ray crystallography for his doctorate, investigating the structures of biological macromolecules such as antibodies. He held a Royal Society University Research Fellowship at Oxford before moving to King's. His research uses X-ray crystallography to determine the structures of antibodies involved in allergic diseases, in particular asthma, in order to develop new therapeutic agents. Brian Sutton is based at the King's Hospital campus in the Randall Division of Cell and Molecular Biophysics, which traces its history back to the Medical Research Council Biophysics Research Unit, in which Rosalind Franklin and Maurice Wilkins worked on DNA under its first director, John Randall. Thank you very much for joining us today, Brian. The floor is yours.
Thank you very much, Birgit, for that introduction. So as we've heard, Rosalind Franklin's science isn't just based around DNA and the famous photograph 51 that we see here on the slide. She worked on coal and carbons and also later on viruses, as we've heard. But the common thread throughout these studies is X-ray crystallography, and that was her science. I actually started learning some X-ray crystallography while she was an undergraduate at Cambridge, and these are some of her notebooks. She's taking a course at the Cavendish on crystal structures, and you can see her sketches of various crystal structures here. And on another page, I'm intrigued to see that there's a particular, this discusses particular ways of packing molecules in cells, in crystals. And symmetry is something that obsesses most crystallographers. And this particular way of packing molecules, C2, we shall come back to a little bit later, because this happens to be the symmetry of the DNA molecule. On another page of her notebooks, it's fascinating to see that she's learning about nucleic acids and makes a comment to herself, geometrical basis for inheritance. And what a remarkable thing to read. This is in 1939 or 40. Just a little over 10 years later, she was to take an X-ray photograph, which was to solve the problem of the structure of DNA, the nature of the gene. And indeed, we discovered that the basis for inheritance is indeed, in a sense, very true, very real sense, geometrical. So what is X-ray crystallography? Well, crystals, when you fire X-rays at crystals, you get beautiful diffraction patterns such as this. X-ray diffraction patterns are not like medical X-rays. You don't get a shadow of the structure, a diffraction event which involves interference of waves scattered by the atoms in the molecules in the crystal. You get these beautiful diffraction patterns, and the crystallographer's job is to measure the positions and intensities, the blackness of each of these different spots, and do a calculation to work out what the structure is that's causing the diffraction. This is difficult enough nowadays with computers, an extraordinarily difficult job in the time before computers when everything had to be done manually. Well, that's a beautiful diffraction pattern from a crystal. Coal, you might think, might give perhaps not such a beautiful diffraction pattern, and you'd be right. The diffraction patterns you get from coal, such as these taken by Rosalind Franklin when she was in Paris in Jacques Mering's lab, are far from as beautiful as the ones I've just shown you. But what you see are arcs. These arcs tell you about repetitious structures, regular structures in the coal. So although the coal is in a rather amorphous, irregular structure, it does have regular structural features. And what she was doing was studying what happens when you heat coal to very high temperatures and cooling it, and seeing whether or not it turns to graphite. And so this is a sketch of the sort of structures that she envisaged the coal undertaking, taking up as it was heated to high temperature and then cooled. Graphite, as some of you may know, is a structure in which rings of carbon are packed against each other, and she could tell from the diffraction patterns to what extent graphite was being formed. We've heard how important coal was, certainly in wartime and after the war, and she introduced the concept of understanding the she understood the microstructure of coal and its relationship to its calorific value. As we've heard, she moved from Paris after 4 years of working in Paris. I should say she'd already become an international expert in the field, quite remarkably, and she published many papers and was invited to conferences. So she'd already established a reputation in this field, and she was invited to join King's, where X-ray diffraction studies of DNA were being carried out by Maurice Wilkins, who took this photograph in 1951. The fact that you get a diffraction pattern like this at all is very exciting, because it shows that DNA has a regular structure and could be determined. And Rosalind was undoubtedly invited to King's by John Randall, head of the lab, because she had this experience of not perfect crystals, but partially disordered systems. Her training in crystallography was rather unusual in that she didn't work with perfect crystals, she worked with partially disordered systems. And that's true also of the virus work. So here we see typical setup that she used. The camera is here. It doesn't look much like a camera, but it's the camera which holds the film and the specimen. The X-rays are generated somewhere behind all of this lead shielding here, and they're fired into the camera, and the X-ray photograph is taken. But the camera is flushed through with hydrogen gas, which is passed in turn, well, before it goes into the camera, through salt solutions that enable the humidity of the gas to be changed. And this was really crucial. And what I want to really say is that she was a superb experimentalist, and she realized that you had to control the humidity and the water content of the X-ray, of the DNA fibers, which I'll speak about in a second. And it was through changing this systematically that she discovered the two forms of DNA that I'll talk about in a moment. These specimens are quite remarkable. The DNA is purified as a white solid, and these are samples that date back to the 1950s. What she would do would be to take a small amount of this white solid, put it on a slide, add a drop of distilled water, make a gel, and then out of that gel pull a very, very fine fiber. She was very, very good at this. You didn't want the fibers to be too thick, you didn't want them to be too thin. There's a famous exhibit sitting next to it, which is a strand of DNA stretched onto a bent paper clip, in fact by Maurice Wilkins. This is nearly 70 years old, and if you look very, very carefully, you can still see the strand of DNA sitting there. The fibers of DNA were inserted just behind the collimator in the camera. This is a smaller camera than the one I just showed you, but this is the one that was used to take photograph 51. And the film is very small. The piece of film, the X-ray film on which photograph 51 was recorded was just 2 by 3 centimeters. So this is a shot of the notebook, Rosalind's notebook for May 1952. She's doing a series of experiments with different humidities, and here's experiment 51, hence the name of the photograph. Started on the 2nd of May 1952. She finished the exposure for 4 days later. There was an interruption, so that the total exposure time, total time that the X-ray fiber was exposed to X-rays was 62 hours. And the result was the famous photograph 51. This photograph with its X pattern tells you that the likely structure of the molecule is a helix, and that won't be obvious to most of you. I'd be happy to talk about that later, how to read this photograph. But you must realize that she had a whole series of different photographs with different humidities, drier ones and wetter ones. And the B form, she called this the A form and the B form. And photograph 51 is the best example that she ever obtained of the B form, the wet, high humidity form of DNA. But she had A form, drier photographs to look at. And if you're a crystallographer, which one would you go for? Well, you would go for the one on the left, because there are so many more spots, so much more information, so much more opportunity, likelihood of being able to calculate your way back from the diffraction pattern to the structure. So she concentrated on the A form and put the B form away for a while. She knew more about the structure than that. She knew about the symmetry, and here is space group, as we call it, C2. That's the packing of the molecules, or the symmetry of the molecules. So C2 appears again, and that's something we can talk about a little bit later. She was unhappy at King's, as we've heard, and she was planning her move to Birkbeck. And just before she left King's, she turned back to structure B, photograph 51, and started analysis. And it's really intriguing to see how far she got in her analysis and her thinking about what the structure of the B form of DNA might be from photograph 51. In this draft of a paper, which drafted with Ray Gosling, the structure is helical. The phosphate groups lie on the outside. She determines the diameter and the pitch of the helix and the fact that there are 10 units per turn. But even more remarkably, she says that if there are two strands of DNA, then they must be offset by each other by 3/8 of the fiber axis period. In other words, if you think about the DNA structure, the two strands are not equally separated from each other. One is slightly closer, if you like, to the other. So she was very, very close to the answer. But by now she's in Birkbeck, looking at viruses. Well, viruses, of course, are so topical now, and we've all seen pictures of viruses. The virus she worked on was the workhorse of the it was the first virus ever to be discovered. In fact, TMV, tobacco mosaic virus, a rod-shaped virus. Viruses are essentially nucleic acids, RNA or DNA, enclosed in a protein coat. Not all are rod-shaped, of course. Some are spherical, as we know from coronavirus. This plant virus is also spherical, and the human polio virus is also spherical. And the spherical viruses can be persuaded to crystallize. But tobacco mosaic virus, with its rod-shaped structure, needs to be teased into almost like fibers again. So we're back to her skill in drawing out fibers, aligning. That's wrong to call them fibers, but what you need to do is to align all of these rod-shaped viruses similarly. And she managed to do that and take very detailed X-ray diffraction photographs such as this. And you can see so much detail in this. This is one of her diffraction photographs of TMV. So many data points, so you can well understand that measuring those data and calculating your way to the structure is a possibility. And so she was the first person ever to come up with a detailed structure of a virus. And this model that was built shows the helix, the black piece in the middle is a helical array, a helical piece of RNA surrounded by the protein coat. It's also the first ever self-assembling molecular system that was discovered. Later on, many years later, using X-ray crystallography, more detailed pictures emerged to show that this was essentially right. But she was seeing for the very first time the interaction between nucleic acid inside a virus and protein. She also worked on the spherical viruses, got beautiful diffraction patterns with very interesting symmetries. You won't be able to read all the numbers around the edges of the picture on the left, but there's a 5 and a 3 and a 2. Those are rotational symmetry axes, and you can see my fascination with symmetry. This showed her that the structure was icosahedral, because an icosahedron has a 3-fold axis of symmetry in the middle. If you rotate it by a third of a turn, it looks the same. Each of the triangular faces has a 3-fold axis of symmetry. There are also 5-fold axes of symmetry, and there are also 2-fold axes of symmetry. So this 5-3-2 symmetry shows that it's icosahedral, and again, models were built of what these viruses might look like. Polio virus she was working on at the very end of her life, and she never got to see the final structure. That also is an icosahedral virus structure. And now, much later, we have a high-resolution structure showing at atomic resolution the icosahedral shape of the virus. And you can even see, if you look carefully, the five-fold symmetry in the middle. One of her colleagues, Erin Klug, in the group that she put together at King's, at Birkbeck, said of her afterwards, "She worked beautifully. Her single-mindedness made her a first-class experimentalist with the sort of skill that blends intelligence and determination." Erin Klug was awarded the Nobel Prize in 1982 in part for his virus work, and in his Nobel acceptance speech, he fulsomely praised Franklin's contributions and said, "Franklin herself might have stood on this platform had her life not been cut tragically short." But I'll leave the last word to Rosalind herself.
Science and everyday life cannot and should not be separated.
Thank you.
Thank you so much, Brian, for these fantastic visuals. In fact, Patricia, if I could ask you to come back into our view as well.
I think I am.
You are now. Hello.
Yeah.
And Brian, if I could start us off on a conversation, and audiences, please do put some questions you have for either Brian or Patricia into the chat, and we can pick up on them, or obviously if something occurs to you while we're having a conversation. But if I could just interrogate a bit more we will have a lot of visual elements later on in the presentations and musical elements. So if Brian, if you could help us a little bit to unravel some of this, what do we see in photo 51, which I personally, I think is, everybody is such an icon of scientific research. Could you help us a bit more to interpret this photograph, looking at it very closely?
Yes, certainly. As I said, X-ray diffraction photographs are not in any sense a shadow of the structure, so you can't look at it intently and see the structure. Spots in diffraction patterns tell you about regularities in the structure. So if there's a regularity, a repeating motif, if you like, in the structure, it's going to lead to a spot or a series of spots on the film. So what I need to remind you is that in the setup, the X-rays hit the DNA molecule, or the many DNA molecules in the fiber in the fiber of DNA at right angles. So the fiber axis, if you like, is vertical, and the X-rays come this way. So the X-rays we're seeing in the photograph 51, we're seeing the double helix from the side. So imagine what a helix looks like if you look at it from the side, or if you like in projection. It looks like a zigzag. You can't see the helix, but you can see a sort of zigzag pattern, and the zigs going this way, if you like, and the zags going that way are a regular repeating motif. And they lead to the two rows of spots which intersect at the center of the pattern and give you the cross. So when I look at the pattern, the X-ray pattern, and I see the cross, I think of two intersecting planes, sets of planes, which is what the molecule would look like from the side. And so you can't be sure that it's a helix, but it's very likely a helix. So a helix certainly from the side would give that sort of pattern.
Brian,
does that help?
Yeah, it does. But Patricia,
your question, Brian, have I got this right? That if you've got sodium chloride, which is a very, very simple compound with just two kinds of ions, and it's as I understand it, it's a series of cubes with an ion on each corner of the cube. Sure. And when you do an X-ray photograph, that just comes out as a lattice of black dots.
A lattice of spots. Yep. Yeah. And
so that's the very, very simplest version.
Absolutely.
You've got a cube, it goes into a two-dimensional picture of a black and white lattice. And then when you imagine something like a double helix, I mean, the complication of working out, relating the structure to the spots is just phenomenal.
Yes. But something I can't resist adding to what you just said is if you take your cubic structure of your cubic crystal, because the crystals are cubic too, of sodium chloride, if you fire the X-rays into a face, that's fourfold symmetric. So the diffraction pattern you get viewing it from that direction has fourfold symmetry. If you fire it into a vertex, you get threefold symmetry, because if you look on a cube down on one of the vertices, it has threefold symmetry. If you fire it into an edge, you get twofold symmetry. It's a bit like the icosahedron with its 5 and its 3 and its 2-fold symmetry. So you can tell, I'm saying that because symmetry is so crucial to all of this. And when you're looking at diffraction patterns, you need to interpret the symmetry as well as the positions of the spots and the intensities.
Why was James Watson so excited when he saw the photograph?
Yeah, well, because it was such a... Yeah, I mean, in longer talks, I give examples of photographs that were taken leading up to photograph 51, in which you get a sort of blurry pattern that maybe is indicative of a cross. The point about photograph 51 is it is so beautifully clear. There's no doubt that there is a cross pattern. Pictures that have been taken up until that time hadn't been so clear. And you could just count the number of spots. You could work out the pitch of the helix. You could work out the diameter of the helix. But the cross was so clear in photograph 51, so much clearer than any previous photograph. Yeah. In fact, it shocked Maurice Wilkins. He was surprised that it had such an effect on Jim Watson, because he imagined that Jim had seen rather similar photographs before, but in fact he hadn't.
But didn't Jim Watson had rather a bad track record? He tended to jump to hasty conclusions, and he'd built some models, and Rosalind Franklin went all the way up to Cambridge to
That's right, yes.
seminar. Yeah. He just immediately demolished it and pointed out where he'd gone completely wrong. So he was probably feeling a bit sore about that. He seems to be a very competitive sort of person, and I think he definitely wanted to get there before her.
That's absolutely right. And they were embarrassed by the mistake that they made 2 years earlier when they built a 3-chain model with the phosphates on the inside and the sugar and the bases on the outside and so on. Completely wrong.
We have some questions from the audience, if we can put those in. There's a question here from Dave.
Oh, I think Franz just got muted. Hang on. I can ask this question, actually, because we wanted to look more fully at Rosalind Franklin's work. So, you already showed the work on viruses. I've got one question here by Shirley Franklin. If Rosalind had not been working on the DNA molecule, would she have got similar recognition for her other, perhaps more significant scientific work?
As I understand it, the work that she did on coal during the war, she did a lot of research into coal and graphite. As I understand it, that's still a sort of fundamental work, rather like her viral work. Is that right, Brian? So
yes, that's right. I even checked the number of citations that a review that she wrote in 1950. That paper on coal has been cited as many times as her paper in Nature that shows photograph 51.
Yeah.
And so her papers are still cited today. So the work she did was remarkable for its time and is still relevant today.
Yeah, I mean, because coal hasn't got the glamour. I mean, you showed us.
No, it hasn't.
It's not as glamorous as the double helix, but it's really important.
It is.
We've got another question here. From Anja, would you say Rosalind should have won a Nobel Prize for the DNA work or for the virus?
Shall I have a go at that?
Yes, please.
Well, Nobel Prizes are never awarded posthumously, and she had died before any of the nominations were ever made for the Nobel Prize for DNA. So in practical terms, the Nobel Committee had an easy time because there were only 3 scientists alive. Had she lived, what would have happened? Well, that's an endless matter of debate. I guess there is one way out. There is more than one prize you could award. Perhaps you could have awarded the prize in chemistry to Franklin and Wilkins, and the prize in physiology or medicine to Watson and Crick. I don't know. But the matter didn't really... But I'm pretty sure, as Aaron Klug says, had she lived, she would have been in line, surely, for a Nobel Prize for the virus work. The only caveat to that is that there were other labs working on virus structures at the time, and so it wasn't, by the time more detailed virus structures were available, there were many labs working in the field. But she certainly initiated the field, and at the time of her death, she was she was the acknowledged world leader of the top team working on structural virology, as we now call it. And all of that has led to what we now vitally need to know about coronavirus and the structures of what that looks like and how that interacts with human cells and so on.
And
So, as I said, yes.
So I was just going to say that Aaron Klug specifically asked to work on her team, and he got the Nobel Prize in 1982. So it does seem very likely that she would have done as well.
Yes, I agree.
Another question here, would new technology have impacted her work?
I'm sure computers would have made a colossal difference. I remember reading some accounts. She went out to dinner with a friend, and she brought her sort of hand calculator with her, and she was sitting at the dinner table, sort of turning the handle and pounding away at numbers. I think computers presumably made an enormous difference.
Computers made the biggest difference, yes. Yeah. Yes, and that was happened just a few years later.
Yeah.
Doing those calculations, those Fourier calculations, to get from the diffraction pattern data to the structure, to be done by hand, you just need a lot of work on an adding machine.
There's one question here which is in two parts. Is there any record of anything Rosalind said about her stay in Paris? And was there any work she did while she was in Paris? I think you've answered the second part, I think, already.
There's a lot of records of when she was in Paris. I mean, she had a very, very happy time there. And there's a very sad letter that she wrote to her elder brother, Colin, while she was still in Paris. But when she'd made the decision to leave, but hadn't actually gone. And she wrote and she said, I think this is one of the biggest mistakes in my life. I'm so happy in Paris. I feel that I've made the wrong decision to go to King's College. So if she hadn't gone, I mean, obviously her whole life would have been different, but she was doing very important work there. And she was very happy. She had lots of friends and she was very well accepted in the laboratory, and she was already on a rising career trajectory.
Yes.
The next question is there anything in photo 51 that suggests two helices?
That's a very perceptive question. Yes, there is. If you look at photograph 51, I don't know whether anyone can see it at the moment anywhere, but if you start at the center of the pattern and work your way out along one of the arms of the X, you see the first spot, the second spot, the third spot, but the fourth spot is not there, it's missing. There's a total absence of any intensity at the fourth position. And this is what I was very briefly alluding to when I mentioned at the end of the section on DNA, that she came to the conclusion that it was two chains that were whose patterns, if you like, were interfering with each other and causing the fourth layer line to be absent, the fourth spot to be absent. So the simple answer to the question is yes, there is an indication in the picture that something more than just it's not just simply a single helix.
Could I just go back to Paris for a moment, because I don't know if everybody saw it, but Shirley Franklin inserted a message reminding me that, of course, at Churchill College there's a huge archive of Rosalind Franklin's papers, and that includes a great deal of correspondence with her family while she was in Paris, because as I said, she was very close to her family, and she wrote very emotive letters sort of describing what she was doing. They're fascinating reading.
Yeah, she was a wonderful letter writer.
Yes. And she also, I mean, she wasn't just stuck in the lab all day. She loved going on hiking and mountaineering and cycling and all those sort of outdoor sports. She was very keen on it. She was also very good at things like needlework and dressmaking, and she loved making meals for her friends. So she was a very, very sociable person, a complete contrary to the impression that you get from reading Joan Watson's account of her.
Actually, shall we close this conversation now, Francis? But I'm dying to ask one last question, if I may, is that what has Rosalind Franklin done for women in science? For the perception and for working, for women into becoming more integrated in scientific work, where she's particularly had a hard time working at King's College?
I think she used to be an extremely good role model, because it drew her situation drew a lot of attention to the way that women were routinely discriminated against in science. But it seems to me that it's rather now an outdated role model. If we want to have a role model for young women today, or young girls at school who are considering going into science. We need a more positive image, and to present her as a female victim, in a way as a failure, as someone who's been outlawed, who's discriminated against, is not a very positive role model. What we need is to present her for what she did. She was a world leader in virology, which in 100 years is going to be probably, unfortunately, even more important than it is now, and that would be a much better way to present her to women in science, as somebody who could achieve, who was at the top of her field.
Thank you.
I've nothing to add. I couldn't have put it better myself.
Yeah. Thank you. In that spirit, shall we move on and see how Rosalind Franklin has not just inspired scientists and historians of science, but also artists to work with her material. So thank you very much again, Patricia and Brian, for your excellent presentations.
Thank you everybody for your questions.
Yeah, and thank you for your questions. That was excellent. So, you know, keep on thinking. You can always put them in the chat, and there might be other moments later where we can build them in. Now, I would like to introduce a piece that was produced during lockdown by Francis M. Lynch, who worked with Brian Sutton and artist Shelley James, where he collaborated to reflect on the work on Franklin as overall, but particularly focusing on the tobacco mosaic virus. Before you watch the short film, I'd just like to say a few words on how this collaboration was generated in lockdown. It was using a new technology, Zoom, and that's how I think is how you probably perceive it somewhat in the film as well, which we're going to see now, and then we have a conversation with the artist.
We are at war.
There has been war for billions of years.
There has been war between virus
There has
and
been war
bacteria.
for billions of years.
There has been war between viruses
There
and
has been
bacteria.
war
There
between
has
viruses
been war for
and
billions
bacteria.
of years.
There has been
There
war
has been
between
war
virus
between
and
virus
bacteria.
and bacterium.
There has been war
There has been war
even before
There
our
has been
time.
before our
There has
time.
been war between virus and bacteria.
War is older than RNA.
War is older than DNA.
War for billions of years between
billions
viruses
of
and
years old.
bacteria.
War between virus and
Between
bacteria.
virus
our time.
and bacterium. We are at war before time.
Before time.
Before time.
Virus before time.
Virus
Before
before
time.
time.
Bacteria before time. Bacteria before time.
Polio, the first human virus ever crystallized. The first human virus structure ever Polio, an epidemic of the 50s. Salk's vaccination program was in process
In order of
as
magnitude,
Franklin
A
worked to
cell
find the
is
structure of the
approximately
polio virus. After
1/10
all,
of a millimeter.
knowledge of the structure of the
A
virus might
virus
lead to
is
a better vaccine.
1/10,000th of a millimeter.
The icosahedral structure of polio virus was later found for many other viruses.
There has been war between science and
Between
money.
colonizer and colonized.
Cash crops kill.
Tobacco plantation.
Cash crops kill.
Tobacco smoker.
Cash crops kill.
Tobacco mosaic virus.
Cash crops kill.
Tobacco science.
Cash
Tobacco
crops
science.
kill.
Tobacco science.
Cash crops kill.
Plantation, slavery, and death.
Cash crop.
Cash crop.
Cash crop.
There has been war.
Cash between tobacco and lungs. It is believed that the nucleic acid occupies a central position.
Polio, the first human virus ever crystallized. Polio, The first human virus structure ever to be studied. Polio, an epidemic of the 50s.
Structure of tobacco mosaic virus by Dr. Rosalind E. Franklin.
Tobacco mosaic.
Knowledge of the structure of the virus might lead to a better vaccine. The icosahedral structure of polio virus was later found for many other viruses.
A virus is a piece of nucleic acid in a protein coat. A molecular machine converts RNA to protein. It makes its own coat.
Human, a reluctant host. Virus, a determined guest. A virus needs life to replicate.
A reluctant host.
A virus needs cells
Virus,
to replicate.
a determined guest.
A virus needs us to replicate.
A reluctant host.
It cannot live
Virus, a determined guest.
without money. It cannot live without us.
It cannot exist without us. It cannot live without us.
It cannot exist without us. It cannot live without us.
Well, if I can speak for everybody, a round of applause for today's premiere of Virus in Molecular Mode. We are lucky to have both collaborator artists here today. Francis M. Lynch, here we are, and Shelley. James, can I see you?
Are we both here? It's hard to know, isn't it? There's so many people here.
Yeah, I know. So before we head into a short conversation with both, if we can find Shelley, I'd like to just introduce her briefly to you. Shelley James trained in textiles in Paris and began her career as a design consultant, but she now teaches, among others, at the Royal College of Art and has her own artistic, often collaborative practice. As you can see from the film, a fascination with flickering streams of signals that conjure up our experience of a supposed stable world, and experiments with optical illusions in glass, as well as conversation with vision scientists led her to studying for a PhD at the Royal College of Art. Light as a material has become central to Shelley's practice. She now works with scientists, artists, curators, and a growing number of health professionals to explore the way that light literally shapes our world. Thank you very much for both joining us.
Thanks.
I would like to discuss discuss the process of collaborating. You collaborated with Brian Sutton on this piece. How did you collaborate during lockdown to create this new work?
Well, if I can start, Shelley, I think that lockdown has been very interesting for making music, especially with all the singers. You had a lot of voices there. The male voices were the protein coat being built up around the RNA in the centre of the virus, and so they had to record all their parts individually and then send them to us, and then we kind of put them together and produced it that way. So all of it was the process of recording, just that last bit, which we just finished the production this morning, took a very long time. So we actually had a conversation with Brian in early June. So Brian's somebody I've known for a long time, who I met at King's College London when we were doing the first Franklin Effect project, and he talked his way into our project, and we realised that we couldn't live without him. So he's been with us and guiding us and helping us with all sorts of things through this. And he talked to me and Shelley was there as well, on Zoom, obviously, about Franklin and the virus work that she did, and he sent me her papers to read, which I found very useful. And then I made up a score, which I shall show you what it looks like. So it looks a bit like this. It's not really a conventional score. So this is these are the images that Brian said would be the simplest ones for me to use, because obviously they have to be simple for me. And there's the canon that I was doing with the singers, is these protein molecules going round it like a coat, and there's the RNA, which was the solo voice, and there's the RNA. I like this pattern because it shows you the RNA is a single strand, not like DNA, but that it also goes back on itself. So I was able to kind of make patterns which kind of fitted all these shapes, and of course that's Franklin's picture of the virus there, which was also very useful in sort of thinking about, Shelley is brilliant on light. That's her thing. So this was a really interesting one to go with. And then I had there's quite a big score. You can't put it all in one place. And then of course I had a little picture of the tobacco virus and some words, and then more words of Franklin's. And these all provided me with musical and sound worlds, and some more of her pictures there. And then I wrote a couple of things on a piece of manuscript, because I feel if you don't do that, you're not a real composer. You have to write things on a manuscript. So that was my process. And then I sent a kind of, Shelley and I then got together and kind of looked at all these things together. And then she came back with lots of ideas.
Yeah. So, Shelley, do we see you? Here you are. Nice to see you.
Hi. So it's been interesting lockdown because I don't have access to my studio, but I have been working. Again, I've been lucky enough to work with Brian for some time. So as a threesome, we Francis and Brian and I had a conversation about the ideas and about the underlying feelings there. And then I took Francis's script and came up with a series of sketches, and then of different sort of worlds that we might look at, and I then set up a studio in a cupboard here in Bridport, and used some pieces of glass which I've made before. So that's a rhombic triconedron. It's a piece of cut polished glass. It's hot glass that I built up in layers, and then there was this piece, and then this piece, I'm not sure if you can see, so it's got layers of bubbles and structures inside it, which related very closely to the structures that that we was discussing with about the tobacco virus, and a laser pen, and a turntable on an ironing board, and very, very simple, rudimentary, but I suppose I wanted that feeling of a sort of a searchlight in the idea of the war, and it just being very dark and very sort of mysterious, but at the same time very hopeful. So I sent some sketches and then built up a layered piece, which for me reflected the way that Francis was working. And then it was an ongoing conversation via Zoom until we came to something which we both were very happy with. So that was...
I enjoyed it because you can almost sense the laboratory setting. I imagine something that's similar, that Rosalind Franklin would have been of being in her lab and also gazing hours and hours, manipulating materials and textures, and looking through the microscope, which I thought was very very beautiful. I think it feels almost really perfect having a lockdown to make such a piece, because you had just the occasional sort of light shining through, and so I don't know, it's just allegorically it almost functions very well. I think
it was surprising how I was lucky enough to know both Francis and Brian already, but the atmosphere, the sort of feelings they were trying to express, we were able to communicate quite well through the Zoom medium. I was surprised at how well that worked.
I was interested that you picked up particularly on the tobacco mosaic virus. Do you want to talk a bit more about this? But because also you've got some very strong wording attached to this regarding it being a cash crop and slavery and so on. Would you like to elaborate on this a bit?
Yeah, I think I've always been, I suppose I hadn't thought about it too hard until Brian started talking about, war and how virus and bacteria have been at war since the beginning of time, or even before then. And I've always wondered why tobacco virus was the thing that she was studying. It just seemed such an odd thing, you know. So when we think about tobacco now, we think about something very damaging, and you think, well, why would you be studying that? But of course, at the time she was studying it, smoking was huge business economically, and it was one of the first businesses that really made its money, if you like, at the beginning of its life, that business, through getting rid of its indentured servants and bringing in slaves. So it really has a terrible history in so many ways, but that correlation between science and money is a very clear one, and you know, that's obviously at the moment people are being given money to do just, you know, to look at a virus which is attacking the human population, which is a whole different thing. But again, you know, it's about where the money is, isn't it? You know, it's you know, what science can do is all related to that, and I think sometimes that's easy to forget. I mean, I certainly, as a kind of general public person, you know, just assume that scientists are just out there doing their thing, you know, trying to make the world a better place, and that these things don't come into it. And then when I first went to King's College, I think it was the first time I realised that scientists actually have to apply for funding for everything they do. And it just seemed, I don't know, it just opened up my eyes to how this world works. And I thought it was quite an important thing to bring out as well, that, you know, you this correlation between these things sometimes doesn't sit well. But then, of course, she was studying polio as well, which was a virus, you know, that attacked humans. And I also, you know, think to myself, well, thank goodness the money was there for her to study tobacco virus, because, you know, she discovered the structure, and it's been so important to us.
Yeah, it's both aspects of science in society and the funding it needs, as well as public health aspects, like we all now know, because we're all experts on viruses now, aren't we? So, living through the coronavirus pandemic. Are there any questions from the audience that I haven't picked up yet? Otherwise, I would just like to hear a little bit more how you, just as sort of in a technical point, because I think it's fascinating, of how you work with the singers as well, just on a production kind of aspect of this, because we're all sort of having to learn to live with new technologies, and I was just fascinated how it might have influenced the process of making the piece as well.
Well, the singers are all amazing, because you know, we've never been in this situation. We're an ensemble, so we're used to meeting each other and spending hours just exploring a semitone between us, things like that. I mean, you know, we do work a lot together. You know, when we're working, we do a lot of work together, and it was just incredible. They just really stepped up to the plate. I mean, you know, we first started working with Zoom together, and I would send them a track, and they would sing to that, and then they would sing it to me while they played the track, because there's a delay on Zoom and it would all get messed up, and we kind of agreed on what was happening first of all. But with this piece, so we've done quite a lot of recordings now, because we started doing this in May, because we did a festival for Brixworth up in Northamptonshire in May, and we started, I was unearthing a lot of music by women from the 18th century, because we do quite a lot of that in our projects as well. We look at women whose music is quite hard to find, actually, from earlier on in England particularly. I found it difficult. So they were recording those, and actually what's been nice about it is that, especially with this piece, there wasn't really a lot of time, because there were huge amounts of files to be made to make it work, and they really just got on with it on their own, recorded it, and then sent it over to Herbie, who's disappeared. You are there. They sent it over to Herbie, and he sorted out. He does the production, so I do the editing, and then Herbie does all the production. So he then kind of made it all work. So yeah, and then the singers have no idea when they're recording what it's going to be like, because they just get little fragments of bits and say, "Can you do that for me? Can you do that for me?" And they just put their heart and soul into it and send it to you. It's incredible.
Yeah, no, it's a very nice way of understanding, you know, the precision of that, but also how you have to think about the whole texture and structure at the same time. A little bit like looking at the DNA structure, I guess, dare I say. But, you know, I was so struck by the use of the paper clip in science as well. So, you know, there's sort of always there's moments of handmade, and, you know, improvisation in there as well, which I'm glad to see. Material witnesses of. So thank you very much, Frances and Shelley, for premiering Virus in Molecular Mode for us tonight. And congratulations again on the collaboration with Brian and the inspired work that you've been able to show us today. I'm really pleased that we could continue our exploration into Rosalind Franklin's work through your eyes, and now more eyes, sets of eyes. I've now got the great pleasure of introducing composer Shirley Thompson to our event on Rosalind Franklin. Professor Shirley Thompson holds degrees in musicology, modern history, and aesthetics of contemporary classical music with composition. Her passion for music and learning led her to complete a PhD which focused on changing the perception of women in opera. Her doctoral thesis inspired Shirley Thompson to create Heroines of Opera, a series portraying assertive female protagonists. Her varied and groundbreaking career has seen her write, conduct, and stage award-winning classical productions that have been performed at illustrious venues such as London South Bank Centre and the Sydney Opera House. A very warm welcome to you, Shirley Thompson, for joining us tonight. And we look forward to hearing your thoughts on the Franklin effect.
Thank you very much indeed. It's so exciting to be here. It's a great honour because I was introduced to Rosalind Franklin's work through the project of the Minerva Scientifica back in 2013, 2014, I think. So we have been involved in this discovery of Rosalind Franklin's work for some time. Well, for persons like Professor Brian Sutton and others, Patricia Farrer in the field, much longer than myself. It really has been an exciting journey. I'd just like to welcome everybody, and it's great to see all my colleagues, composers, scientists, performers, singers, artists that created costumes for the production of the various projects involved in the Franklin effect. It's an honour to speak on behalf of my dear composer colleagues, whom I'm going to name shortly. But I'd just like to begin by with a little story about the performance of one of the pieces from the CD. A performance of Random Sequences was given by the BBC Singers a couple of years ago, and Fiona Talkington introduced the work from Rosalind Franklin's CD, introduced the work and said, ladies and gentlemen, it's the first time, I can say it's the first time that I've introduced a piece of music that talks about DNA replication and genome coding. The audience twittered away. It was a funny moment, and possibly anticipated what the piece was about. But Fiona Talkington from Radio 3 hasn't forgotten me since then. She always remembers having to introduce that piece, which was pretty unusual. I think it speaks greatly about our achievement of interweaving music and science, important scientific research and groundbreaking music, which was the achievement of the CD, the Franklin effect. My collaborators on the CD includes Cheryl Francis Hode and her piece Photo 51. She collaborated with the renal biologist Dr. Claire Sharp from the Department of Renal Sciences at King's College London. Cheryl draws on Rosalind Franklin's biography, The Dark Lady of DNA by Brenda Maddox. It's quite a wry piece. Lynn Plowman produced a piece, K-Raz, and worked with Professor Elizabeth Kuipers, Elizabeth Kuipers, Professor of Clinical Psychology, and also at King's, and they explored the coding of the KRAS gene, literally. My other colleague, Kate Whiteley, collaborated with Professor Mari Scalariadu. His field is theoretical particle physics and cosmology. They produced a piece called, well, a series of pieces called Theories of Quantum Mechanics, exploring different theories of how the universe works at a quantum level. There are also wonderful works by our very own Frances M. Lynch. She created a piece, for example, called Golden Hands, which looks at a very personal side, the very personal side of Rosalind Franklin, as she was, I understand, a great seamstress, or she likes needlework, very, very detailed work, which seems to relate very, very well to her own very acutely detailed work in science. And Frances also produced Soundscape and a couple of other pieces, so she's been very busy directing us and creating at the same time. I don't know how she does it, but she does. And then on to myself, I produced a piece called Life Sequences with Professor Ellen Solomon, Prince Philip Chair of Genetics, also at King's College London. My piece looks at DNA replication, which is the research from the genetic research of Ellen Solomon. And I specifically followed, collaborated with Ellen on her research journey as she was literally making discoveries towards personalized medicines for cancer patients. So I was absolutely thrilled to be invited onto the Minerva Scientifica team of 4 esteemed composers, exploring current scientific research through music with 4 leading scientists from King's College London. I've collaborated with poets, filmmakers, fine artists, choreographers, dancers previously. This would be the first time that I would be immersed in the world of scientific research, and I was so excited. It was totally unknown territory to me, because up until that time, I hadn't really met many world-leading scientists or scientists. So I was really anticipated what we would produce from this project. We had a series of workshops throughout our research and development time in creating the musical artifacts, the musical artworks. And these workshops really set the bar high in terms of artistic and scientific exposition. It was wonderful to hear about the work and motivation for the research and creativity from each individual scientist, composer, electronic voice theatre performer, and from all scientists and cultural institute personnel. It was also good to see the performances of previous work from the Minerva scientific experience, because we would be building on that, and our work as artists and scientists is always standing on the shoulders of those that come before us. A valuable aspect of the project for me was certainly the immediate vocal performance, the ability to hear how my musical material was sounding pretty immediately. Usually when I create a musical piece, I don't get to hear how it sounds really until the rehearsal, but in workshops, we were able to experiment with compositional material at key stages of creating our pieces. All the workshops offered the opportunity to test material with the vocal expertise of the electronic voice theatre singers. We were afforded a wide range, vocal range from each singer with very particular individual skills in producing vocal work. And they were very open to vocal ideas, and they absorbed ideas very quickly, interpreted our music superbly. And this was a terrific asset in developing our pieces, I believe. It was also great to have Judith Weir as a mentor to the project, providing us with providing an expert soundboard to our compositional ideas as they evolved. I felt the experience of working with scientists and other composers, like-minded composers, was really special and historic. It was also very special to be introduced to the work of several world-leading scientists, and then to collaborate intensely with a single scientist, exploring their contribution to the scientific community and raising the awareness and knowledge of several other female scientists that have been neglected in the way that history is told about female scientists. I felt that we all bonded in a true and genuine collaborative spirit. This between the composers, scientists, performers, mentors, and the other artists involved in the project. Being immersed in the scientific ideas and being able to distill and transpose those ideas into a complete piece of music was for me absolutely thrilling and exciting. I was delighted that Professor Solomon, with whom I was working, felt that my distillation of her research narrative into text for musical composition in my piece, Random Sequences, or Life Sequences is the full title, enabled her to distill her thoughts for a proposal that she was making to the scientific community. Overall, the project enabled us, I think, to experience steep learning and a steep creative curve. It's like we all learned so much from the experience. I'm particularly pleased that the project is helping to raise the profile of both female composers and scientists. Rosalind Franklin has been a real catalyst for the project and continues to be an amazing inspiration to us all. Thank you very much.
Thank you so much, Shirley, for those unique insights into this project, but also for the combative words for Rosalind Franklin and the role of women in science and in contemporary music. So I would like to do an introduction for the Franklin effect, but slightly differently, but also drawing attention to what is also needed when you produce music, because you need a producer and you need to distribute it. So our sort of last small contribution to this is First Hand Records, who worked on the Franklin effect film, which we're about to see. So I'd like to say a few words about First Hand Records before we then go into, Jonathan Mayer from First Hand Records will also join us on film before we then see the Franklin effect, and that will be our main part of the performance tonight. So First Hand Records is Jonathan Mayer and David Murphy, who since 2008 have released some of the finest quality classical world and jazz recordings performed by some of the greatest artists. First Hand Records has established itself as a significant independent record label. Its production, as you will see in the Franklin effect, are made with enthusiasm and dedication to create productions that are of high aesthetic value. So we will first show you a filmed introduction to the Franklin effect by Jonathan Myers. And then we will show you, after a sort of a short interlude, we will show you the film.
Good evening, everyone, and welcome to the Rosalind Franklin Centenary Celebration and the world premiere performance of the Franklin Effect, which is part of Minerva Scientifica, an evolving project looking at British women scientists through the music of British women composers, and all inspired by that famous photograph number 51 by Rosalind Franklin. So the Franklin Effect began in 2014, and by 2015, late 2015, we were in contact with Electric Voice Theatre at the idea of releasing a recording, which was done in June 2016, of the Franklin Effect. So things moved at quite a fast pace. The artwork started to come together, and started to realize that it's such a wonderful project. I mean, the concept behind it is fantastic, and it includes some wonderful compositions by Francis Lynch, Cheryl Francis Hode, Lynn Plowman, Shirley Thompson, and Kate Whitley. So I do hope you enjoy this world premiere performance, and from everyone at First Hand Records, thank you very much.
Rosalind Franklin,
Mary Somerville,
1920 to 1958.
Eleanor Davies Colley, 1780 to 1870.
She worked using X-ray crystallography to gather the data to understand the structure of DNA, and her data allowed her and others to discover the structure of DNA.
Emily du Châtelet.
She hugely inspired me as a young potential scientist. Rosalind Franklin, X-ray crystallographer, 1920 to 1958.
Rosalind Franklin, 1831. Arthur Ayrton, 1850 to 1973.
Rosalind Franklin, X-ray crystallographer, 1920 to 1958.
Fixed her steady eyes like X-rays, X-rays on the human specimen before her. Directly give us her data. For that matter, no one at King's realized they were in her hands. it has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material.
While the biological properties of deoxypentose nucleic acid suggests a molecular structure containing great complexity.
Great complexity.
X-ray diffraction studies described here show the basic molecular configuration has great
simplicity.
While the biological properties of deoxypentose nucleic acid suggest a molecular structure containing great complexity.
Great complexity.
X-ray diffraction studies described here show the basic molecular configuration has great
simplicity.
The instant I saw the picture, my mouth fell open and my pulse began to race. Ooh, ah, ooh, ah. Ba-do, ba-do.
A T G GCT, GAC, CCT, GAA, TCA, GCA, AAG, ACA, AGA, CAG. Every time a cell divides, makes a copy. 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 Copy. DNA is present in every cell, blood, bone, brain, breast. DNA is present in every cell, blood, bone, brain, breast. DNA is present in every cell, blood, bone, brain, breast. Blood, bone, brain, breast.
Most often in cell division, an exact copy is made of the DNA. Randomly, mutations occur, and the cell with the mutation can become a tumor or cancer.
Random changes. For many years we have been looking at the changes in the cell.
Random changes.
For many years we have been looking at the changes in the cell.
Genome exploration is helping us with answers. Random changes.
Through genome sequencing of tumors, we can discern the different kinds of mutations and divide them into types such as leukemia or breast cancer. We can now provide personalized medicine and treat our patients with drugs targeted to their own mutations. Genome sequencing is essential to understand cell mutations and how to treat them.
Geometrogenesis.
How did space and time come about?
Geometrogenesis. No notion, no notion, no notion, no notion of time before there was no notion, no notion, no notion of time before there was 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 no notion, no notion, no notion, no notion of time before there was no notion, no notion, no notion of time before there was of time before there was of time before there was of time before there was.
In string theory, matter consists of one-dimensional objects called strings.
Matter. Matter consists of one-dimensional objects called dimensional. Matter consists of one-dimensional objects called matter. Matter consists of objects called
Matter consists of one-dimensional objects called
matter.
In loop quantum gravity, space-time is composed of elementary discrete bits, visualized as tiny one-dimensional loops.
In causal dynamical triangulations, space-time is considered as a collection of triangles, glued together in a variety of ways.
In causal sets, space-time events are related by a partial order, representing causality relations between them.
Sets are related by a partial order. The sets are related by a partial order. Sets are related by a partial order. Sets are related by Sets are related
Within non-commutative geometry, the universe can be seen as a vibrating membrane, a tambourine.
you hear the shape of a drum? If you had a drum played in the next door room, just from hearing it. If you had a drum played in the next door room,
just from hearing the frequency.
Can you hear the shape of a drum? Can you work out its shape? Can you work out its shape?
So we ask, can we hear the shape of our universe?
She was a Scottish science writer and polymathematician.
Edith Cavell, 1865 to 1915, nurse.
She comes from Folkestone in Kent.
Margaret Cavendish, 1623
So she got a job there,
to 17.
and she was put on
Mary Anning,
working with them.
Anna Ashton, 1799 to 1847.
Basically, they
British fossil collector and paleontologist.
Margaret Cavendish.
Franklin was an X-ray crystallographer.
Carolyn Herschel,
She was studying the structure of the DNA molecule, and it's the structure of the DNA molecule that really enables it to function as it does. So it's really important to understand the structure, otherwise we would never have been able to understand how it can be replicated.
1850 to 1852.
She was working on taking photographs at microscopic levels and looking at the patterns of the way X-rays were reflected off of the molecule to give them an
Rosalind
idea.
Franklin, 1920 to 1958, biophysicist.
And it was known before then that there was a backbone with these 4 bases coming off, and everyone was assuming that the backbone was on the inside and the bases stuck out on the outside. And actually what Rosalind Franklin's work confirmed was that the backbone was on the outside and the bases were on the inside, which allowed them to pair with each other, because if they'd been sticking outwards, they'd have never been able to pair.
Rosalind Franklin, 1920 to 1958,
Mary
biophysicist.
Colley, 1874 1780 to 1872.
Elsie Widdowson,
Mary
1908
Scottish science writer and polymathematician.
Mary Somerville, 1780 to 1872, mathematician.
1857 to 1911.
Alice Evans, 1881 to 1975, bacteriologist.
Rosalind Franklin, X-ray crystallographer,
Wilhelmina
1920 to 1958.
1857 to
Her data confirmed the model that Watson and Crick thought up, and it was the data that really convinced the rest of the world that this model was correct.
Caroline Herschel,
Eleanor Davis Collins, 1874 to 1934, surgeon.
Elizabeth Garrett Anderson, 1836
Rosalind Franklin, X-ray crystallographer, 1920 to 1958.
Golden hand, golden hand. Fact, experience, and experiment. Fact, experience, and experiment. Important biological object. Fact, come in pairs. Important biological object. Fact, come in pairs. Important biological objects 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 come in pairs. Adenine, guanine, adenine, guanine, come pairs, thymine, cytosine, adenine, guanine, thymine, cytosine, adenine, guanine, thymine, cytosine, come in pairs, come in pairs, come in pairs, come in pairs.
In nature's infinite book of secrecy, a little I can read.
Very pretty, but how are you going to prove it? Golden hand, golden hand. She was always such stuff with her, such stuff, such dreams always Science and everyday life cannot and should not be separated.
In nature's infinite book of secrecy, a little I can read.
She was always good at sewing. She was always good at sewing.
The brain is wider than the skull.
The brain is wider
The brain is wider than the skull. The brain is wider than the skull. The brain is wider than the skull.
Still the swallowtail flies the fenlands. Still the swallowtail flies the fenlands. Still the swallowtail flies the fenlands. All around the Norfolk Broads. All around the Norfolk Broads. Rosalind, 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 Dr. Rosalind Franklin, Dr. Rosalind Franklin, X-ray Rosalind Franklin, X-ray Rosalind Franklin, X-ray Rosalind Franklin, X-ray. She just a photo. 51, photograph 51.
That proves the structure of DNA. Dr. Rosalind Franklin, X-ray, crystallographer. X is the clue to the double helix. X is the clue to the double helix. Deoxyribonucleic acid, deoxyribonucleic acid, deoxyribonucleic acid, deoxyribonucleic acid, deoxyribonucleic acid, Dr. Rosalind Franklin, X-ray,
break
crystallographer.
break the code, break the code, break the code, break the code and find out who you are. Break the code and find out who you are. DNA in every cell of DNA in every cell of every plant and every cell. DNA in every cell of every plant and animal. A-G-A-C-T-A, genes are sections of DNA. A-G-A-C-T-A, genes are sections of DNA.
Genes are sections of DNA. Copy. Divide. Divide.
Oops, a mistake. Oops, a mistake. Evolution.
Rosalind Franklin, molecular biologist and crystallographer, whose photo 51 was the key to unlocking the mystery of the structure of DNA.
In nature's infinite book of secrecy, a little I can read.
Shakespeare streamed through her life, and therefore her science.
Science and everyday life cannot and should not be separated. Science for me gives a partial explanation of life. Insofar as it goes, it is based on fact, experience and experiment.
Everyday life for Franklin included indulging her family passion for climbing mountains.
The sheer beauty of it made me weep. Mère de nuage.
She was not quite so struck by the beauty of the model of DNA built by Professors Crick and Watson.
Very pretty. But how are you going to prove it?
Photograph 51.
The contribution of women in science can be overlooked.
This is beginning to change.
Not before time.
This is beginning to change.
There is still a long way to go.
1952. King's College London, Rosalind Franklin takes photograph 51.
The key to unlocking the mystery of the structure of DNA.
1953.
We discover the secret of life!
1958. On seeing her laboratory soon after Rosalind's early death from cancer, Her mother remarked she was always good at sewing.
1962. We received the Nobel Prize.
The contribution of women in science can be overlooked.
1968, the double helix. My personal account of the discovery of the structure of DNA.
Based on crystal radiograph 51, taken in 1952 by Rosalind Franklin.
The Franklin effect begins to seep through the cracks.
1964. Jennifer Harvey discovers the first RAS gene.
1983, Claire Sharp reads The Double Helix by James Watson and becomes inspired by Rosalind Franklin's story.
1985, Sharp is accepted at medical school.
1989, the crystal structure of the KRAS gene is discovered.
2004, Dr. Claire Sharp becomes a consultant in kidney medicine at King's College London.
2012, she discovers that DNA drugs against KRAS can reduce scarring in kidney disease.
2015, Sharp's research twists and turns on the double helix of the Franklin effect.
The effect of discovering the structure of DNA was to reveal the mechanism by which this molecule could be replicated.
The Franklin effect swells to a steady flow,
streaming through the countless corridors of King's College London.
A rush of inspiration spreading through the veins of research.
It finds Professor Ellen Solomon as she enters the field of genetics.
At a time when scientists were realizing that genetic disease is due to errors in the DNA replication and repair process. Two rivers flow side by side, each carrying the tiniest particles of life, dredging the sands of time following their respective courses, both shaped by scientific curiosity, constantly refreshed in streams of analytical thought.
1952,
2015,
King's College London. Dr. Rosalind Franklin,
Professor Mary Saccariadu,
molecular biologist and crystallographer,
theoretical physicist and cosmologist.
Franklin seeks to understand the fine molecular structure of DNA.
Saccariadu's dream is to understand the fabric of the universe.
Rosalind Franklin,
Caroline Herschel, 1750 to 1848.
Greece,
Runner of the Louise Bourgeois, 14 Nebula, 1563 to 1636. Midwife. L.C. Widdowson, 1908 to 2000. Kathleen Chemistry at Imperial College London, 1972. Early pioneer of X-ray.
Professor Nicky Clayton, born 1962, experimental psychologist.
Virginia Apgar, 1909 to 1974.
Rosalind Franklin, 1920 to 1958. She worked in a difficult era for a woman. She understood her science absolutely and was one of the best around at the time, but nonetheless never received the accolade that was due to her. And I feel obliged to carry on in her footsteps and put some of those wrongs to right.
Thank you. On behalf of Electric Voice Theatre, I would like to thank all contributors today, and we particularly wish to thank Lauren Lister, our British Sign Language interpreter. There she is. Thank you, Lauren. That was fantastic for her contribution. And finally, I'd like to thank you, our audience, for joining us today in the celebration of Rosalind Franklin. So a big applause. Thank you. Happy birthday, Rosalind Franklin.